In this video, we continue with our discussion on the sampling distribution of the sample mean in the particular case when the parent population does not have a normal distribution, but the sample size n is greater than 30. In this instance, the theorem or statistical truth known as the central limit theorem for sample means applies. And what does it say? It says that if we have a random variable that has a distribution that is not normal, so it's not the parent population or the original distribution is not having the normal distribution, well, we still have the mean, we still have the standard deviation, but there is no indicator that the parent distribution is normal. Well, if we continue to draw repeated sample sizes of size n, then as this sample size increases, the distribution of the sample means would eventually tend to be normally distributed. This is called the central limit theorem. Again, stated in other words, the central limit theorem for sample means says that if we keep drawing larger and larger samples from a particular population whose shape is originally unknown, and we keep calculating the means, the sample means themselves will form their own normal distribution, which would represent the shape or characteristics of the sampling distribution of the sample means. So it is important to realize that the variable n is the number of values that are being averaged together to get the sample mean for each possible sample that is drawn from the population. These should not be confused with m, the number of times we repeatedly pick a sample of a fixed size n. So, in other words, if I pick the first sample, so sample 1, and it has maybe say n equals 35 data values, and I get the average, x bar 1, I can get another sample, sample 2. Again, let's say I still have n equals 35. I average over all of these 35 values, I get the average. I can continue this process, let's say 1,000 times, so sample 1,000, in which case this m right here will be the number of times I drew a sample, each having size 35. And so if for the 1,000th possible sample of 35 units, I compute an average, I will have the 1,000th what? The 1,000th sample average. If I collect all of these 1,000 averages together and I plot a histogram of them, then it should form a normal distribution for possible values of x bar. Take note that this distribution, let me draw it in this shape, this distribution of x bar is called the sampling distribution of the sample means. And it approaches the normal distribution regardless of the shape of the parent distribution. Let's see what this means in problem solving. We take an example. The following histogram represents the population distribution of 600 of the weights of 600 horse jockeys. The mean of the population is 116.2 pounds, and the standard deviation is 3.9 pounds. We are to consider the sampling distribution of the sample means for samples of size n equals 45. What immediately jumps at us is that this distribution is not a normal or symmetric distribution. Rather, this is a right-skewed distribution. This is a right-skewed distribution. So the parent distribution does not have the characteristics of the normal distribution. Well, that is set. The next thing is, we should note that the sample size is being chosen repeatedly here is size of what? 45. and sampling is with replacement. We did mention that earlier. So question A, can a normal approximation be used for this sampling distribution? The correct answer here is yes. Since our n, which is 45, is greater than 30, a normal approximation can be used. So a normal approximation is approved for approximating the sampling distribution of your X bar. So question B, what is the sampling distribution shape? Since we said we can use a normal approximation, it means that the sampling distribution of X bar will adopt the shape of the normal distribution. So it will have the shape of the normal probability curve. And of course, if it has the shape of the normal probability curve, there will be a center value, which is what question C is asking us. So what is the mean? The mean of all your X bars from what we have done earlier is going to be exactly the same as the parent mean, which is 116.2 pounds. And what will be the standard error or standard deviation of the sampling distribution? The mean of X bar we just found is 116.2. The standard error would be the population standard deviation divided by the square root of n, and that will be, going back, you have the population standard deviation, which is 3.9 divided by the square root of the sample size. The sample size was 45, and that will be equal to 0.5814 approximately. So with that said, we proceed to the next example. In this example, we are given a distribution that has a mean of 40 and a standard deviation of 13. We are to calculate the probability that the sample of size 49 has a sample mean that is greater than 37. So, probability, capital P, that a sample mean, X bar, is greater than 37. This probability is concerned with the probability of the sample mean, not the parent population. So we note a couple of things. That the sample size here, so since n equals 49 is greater than 30, we can use the normal approximation in this case. And the normal approximation would say that for the sampling distribution of the sample mean, we find the mean of all the sample means. It is exactly the same as the population mean. However, the standard error or the standard deviation of the sampling distribution of the sample means is equal to sigma all over the square root of n. That will be 13 divided by the square root of 49. This will be equal to 13 divided by 7. This is equal to 1.85714. Okay? So with these two parameters, let me highlight them, the mean and the standard error, that will be going into StatCrunch to help us. So we're going to have the mean here. Again, take note, the mean is 40, and this is 1.85714. So I have 40 and 1.85714. So 1.85714. Now we want to compute probability of X bar greater than 37. So I'll go back to StatCrunch. So I want greater than or equal to 37, and I will hit compute. So that is 0.9469. So 0.9469. So I have the first one, 0.9469. Then again, the probability that X bar again is at most 43. That means it can be equal to 43, not more than 43, but it could be less than 43. So again, I'll make an adjustment in StatCrunch to less than or equal to 43 and enter. So I have 0.9469 again, and that makes sense. 0.9469. And then again, the probability that it is between these two values, between 37 and 47, and 43 rather, the sample mean. So that will be equal to, going back to StatCrunch, I need to make an adjustment to the interface by clicking on between. So that will adjust between 37 and 43 and compute. You have 0.8938 to 4 decimal places, 0.8938 to 4 decimal places. And then the next one is probability that the sample mean is not more than 35. It could be equal to 35, it could be less than 35, but not more than 35. So I will need to adjust again my interface to the standard interface, and I want less than or equal to, according to the question, less than or equal to 35. So I have 35 and enter. So you have 0.0035, and that is the answer there, 0.0035. With that question completed, we now proceed to the next example. In this example, in the game of roulette, a wheel consists of 38 slots numbered 0, 0, 0, 1, 2, up to 36. To play the game, a metal ball is spun around the wheel and is allowed to fall into one of the numbered slots. If the number of the slot the ball falls into matches the number you selected, you win $35. Otherwise, you lose $35. Based on this information, complete parts A through G below. Question A, construct a probability distribution for the random variable X, the winnings for each spin. So, what are the possible outcomes here? So for the outcomes, you can either be winning or you can be losing. So let's see how that goes. Based on these outcomes, when do we win? When we win, let that be our X, and that will be $35 only if the number you selected is the slot that the ball falls into. Otherwise, we are losing $1, so the winning will be -1. Now, what is the probability associated with getting this $35? It is if out of the 38 slots, so out of 38, you pick one that the ball falls into. So the probability that you win is 1 out of 38, same as 0.0263. Whereas the probability that you lose then will be the remaining 1 minus 0.0263, or same as the remaining 37 over 38, which will give the same as 1 minus 0.0263, and that is equal to 0.9737. Based on this probability distribution, which we have just drawn, this table, so the probability distribution in particular will have the highlighted parts, the possible values of your winning, 35 and -1, and their respective probabilities. We would now like to determine the mean and the standard deviation of the random variable X. Well, to do that, we need to find the mean and the standard deviation. To find the mean, that will be each value, 35 for example, multiplied by its own probability plus -1 multiplied by its own probability. If you carry on this calculation correctly, you will get negative 0.05, which means in the long term, you're expected to lose 5 cents if you continue playing this game forever, infinitely, for a long time. Then for the standard deviation, first we get the variance. The variance will be 35 squared multiplied by 0.0263. That is, each value we used earlier, you square it first before multiplying it, plus negative 1 squared multiplied by 0.9737. So we have that value. You get all of this minus the mean you got earlier, which is negative 0.05 all squared. So this would be equal to 33.1776. Now, once you get the variance, the standard deviation is always the square root of the variance. That will be the square root of 33.176, which is approximately 5.76. Question C. Suppose that you play the game 1,000 times so that the sample size is 100 rather. Describe the sampling distribution of X bar, the mean amount of game won. Well, we'll need to talk about the shape. Since the sample size is greater than 30, it will have the normal probability curve, the shape of the normal probability. Then we'll need to talk about the center. That is the mean of all the possible means. This will be equal to the general population mean, which is negative 0.05. And then we'll need to talk about the measure of spread, which is the standard deviation. That will be, so for the sampling, for the standard error, that will be the population standard deviation divided by the square root of n. That will be 5.76. The population standard deviation divided by the square root of n. Our n in this case is 100. So you have 100 here. So 5.76 divided by the square root of 100, which is 10, that will give 0.576, approximately 0.58 to 2 decimal places, if we so desire. Then, the next question, D, is what is the probability of being ahead after playing the game 100 times? That is, what is the probability that the sample mean, X bar, is greater than 0 for n equals 100? Using the distribution we just described earlier for X bar, the mean of all your X bars is negative 0.05. The standard error is 0.58, and we want to find the probability of greater than 0. X bar is greater than 0. 0 should be somewhere here, and we're interested in the region to the right. So we go back to StatCrunch. So I am going to go to StatCrunch, and in StatCrunch, I have my mean of, again, just to negative 0.05 and the standard deviation of 0.58. If I choose, I can also use 0.576 based on the results I got earlier, the mean and the standard error. And using those two values, I want to compute probability of X bar greater than 0. So X bar greater than or equal to 0, compute. I have 0.4654 from StatCrunch. So the answer in that case is 0.4654. 4654. Then question E. What is the probability of being ahead after playing 300 games? Probability that X bar is greater than 0 when our n is 300. Well, we're still using the normal distribution. The couple of changes that we'll have will not affect the mean. The mean will still be negative 0.05. The standard error is the population standard deviation divided by n. Population standard deviation is 5.76 divided by the square root of 300. And so what is 5.76 divided by the square root of 300? We have 0.33255. That's enough. Okay, then we want to find the probability associated with the number 0. So we want to the right of 0. Okay, and that will be equal to, let's key in these parameters in StatCrunch and this value. Going over to StatCrunch, here we go. We have negative 0.05 and 0.33255, and probability that x is greater than 0, and I will compute that. That gives me 0.4402. So taking that back, 0.4402. Then question F. What is the probability of being ahead after playing the game 1,000 times? Again, probability of x bar greater than 0, this time when n is equal to 1,000. So this will be equal to, looking at the same probability, my mean will still be the same, x bar, and the standard error is 5.76 divided by the square root of 1,000, which is equal to 0.182147. Okay, so I'm going to key those values into StatCrunch. So here we go in StatCrunch. In StatCrunch, I have the mean and I have this new standard error, and I'm computing the same probability. So you have 0.3918. So this is the size of that probability. This is still our 0. And this area, this is equal to, as we saw, 0.3918. 0.3918. What we immediately start observing is that as the sample size, the number of times you play the game, n equals 100, increases to n equals 300, and to n equals 1,000, the probability of being ahead, keeps reducing. So in question C, if we were to compare the results of parts D through F, what lesson does this teach you? Let's write this down. We find out that the probability of being ahead, these are the values we got up here, continues to decrease as the number of games from n equals 100 to n equals 300 to n equals 1,000 increases. That is what we found out. With that said, we proceed to the next example. The branch manager for United Savings and Loan in Seaside, Virginia, has worked with employees in an effort to reduce the waiting time for customers at the bank. She and the team concluded that the average waiting time is now down to 3.5 minutes. So, in general, they are claiming that this is now 3.5 minutes with a standard deviation of 1.0 minutes, or 1.0 minutes rather. However, before making a statement at a manager's meeting, this branch manager wanted to double check that the process was working as thought. So what does she do? To make this check, she randomly sampled 35 customers, n equals 35, and recorded the time they had to wait. She discovered that the mean wait time for this sample of 42 customers was 4.2 minutes. Based on the team's claims, remember, the team's claims was it is 3.5 on average and with a standard deviation of 1.0 minutes. So based on the team's claims about the waiting time, what is the probability that a sample mean, x bar, for a random sample of n equals 35 people will be as large, that is equal to 4.2 minutes, or larger than or greater than 4.2 minutes? This is the question we want to first confront. This is the first part of the question being highlighted. The second part would be, what should the manager conclude based on this data? So let's begin our work. In this case, we would like to compute the probability associated with the sample mean. So we need the sampling distribution of X bar. First of all, we note that the sample size being drawn is 35. This is definitely greater than 30. So even though we don't know the parent distribution, we can take it that we can use the normal model. And that means we can use the normal model to approximate the sampling distribution of X bar, where the mean of all our X bar is the hypothesized mean of 3.5, and the standard error will be population standard deviation divided by square root of n. That will be 1 divided by the square root of 35, and that is equal to 0.169. Okay, so based on this, I would now like to compute the probability of X bar greater than 4.2. That means I can locate the possible value 4.2, and then I'm interested in the area to the right of 4.2. So to the right of 4.2. And with that said, I can do this. I can go to StatCrunch to help me compute the size of this probability area. So the mean is 3.5 and 0.169. 3.5 and 0.169. And I'm interested in the probability greater than or equal to 4.2. So greater than or equal to 4.2 and compute. So you have 0.401721. So I have 0.00001721. This is about 1721 out of 1, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So 3, 3. So this means there is a 1,722 chance out of 100 million chances that you would observe a number 4.2 or greater than 4.2. Well, what did we learn earlier? The branch manager actually discovered that for the sample of 35 customers, she actually got 4.2. These should occur 1,721 times out of 100 million trials of this kind of experiment. This probability is extremely lesser than 0.05. So this is a very highly unusual mean of 4.2. That is what this probability value is telling us. If the manager has observed this very highly unusual value, there are two possible scenarios. That is, going to the part of the question where we want to note what the manager should conclude based on this data. Based on the results that have been observed, here are a couple of things that might be happening here. Remember that the team assumed that it is 3.5, that the mean waiting time is 3.5, and the standard deviation was 1 minute. If you are observing 4.2, which the probability tells us that is a very, very, very highly unusual mean, then either the mean and standard deviation are no longer what is claimed to be, or the sample the manager selected is not a random sample. And based on these findings, the manager may conclude, based on this data, that the mean waiting time might have increased beyond the assumed 3.5 minutes. This is what statistically can be implied from this data set.